All right, welcome to lesson 11, 4.11. We're going to continue looking at inverse functions, and I want to point out that I'm going to go over the definition of inverse functions again. I'm going to sort of review some of the stuff that we talked about in class today. And so if you feel really confident in it, you might just take a glance at some of the definition again, just to make sure you feel really confident in it, and then you can go ahead and skip ahead to the problems that you'll want to complete. However, if you are feeling like you'd like a little more clarification, certainly go ahead and watch the entirety of the video and then complete the problems at the end. So I want to just allow you to go back to the discovery problem to kind of refamiliarize yourself with the motivation behind the inverse function, and that we needed to create a function for L in terms of t to cut down on the amount of work that we were going to do to find the lengths of pendulums given times for their period. And this is the process that we're going to continue doing regardless of the function we're working with when we're finding an inverse, right? Changing the role of the variables to create a new function. So keeping that in mind as you go through your work with general functions and finding inverses will be really helpful because it'll allow you to make sense of the domains and the ranges and things like that. So just a good thing to remind yourself, and now we'll get back into the definition that I will go over one more time. If you feel really confident in it, don't worry about it. Go ahead and skip through to the problems that you want to complete. So here's the definition of an inverse function. So if you start with a function f that maps a value of x to a corresponding value of y, let me denote that here. Take a value of x and the function f will map it to a corresponding value of y. Then the inverse of f, or f raised to the negative 1 as it's written, maps a value of y to a corresponding value of x. So what we can say is the inverse will take some value of y and map it to a corresponding value of x. Now I want you to go back to your discovery problem and relate this to the discovery problem. What we started with was a function that gave you t in terms of L. In other words, if you input an L value, your function would take that L value and map it to a corresponding t value. Then we found the inverse so that we could then input a t value and map it to a corresponding L value. Now it's usually helpful to see this done in an example so that you can then sort of put together how this works. So we're going to start with a function f of x as defined by the square root of x minus 2. And if our goal is to find the inverse, what I want you to first think about is if we have a square root function, the inverse should be what type of function? Well, it should be a squared function, right? Or a quadratic. And so knowing that ahead of time is going to make it very helpful. All right. Now, what I want to do is the same process that I went through in the discovery problem. I want to solve for the variable that is currently the input variable, or the independent variable, right? Because I'm reversing the roles of x and y. So it is helpful to rewrite, using function notation, f of x as y, square root of x minus 2. And my goal now is to solve for x, so that I can have a function that does the opposite of what this original function does. So I'm going to square both sides. That leaves me with y squared equals x minus 2. Then I'm going to add 2 to both sides. And this leaves me with x all by itself. So x is equal to y squared plus 2. And here I can see that I have the inverse of my original function. Now, at this point, what I want to do is rewrite using function notation. And the reason I want to do that is that I always want to have my input variable be listed as x. That'll help us out when we go to graph these functions. So I'm going to rewrite this scenario here using my inverse notation so that I can change the input variable back to x. So notice that what I'm going to do is I'm going to input my variable, square it, and then add 2. I just want to change that input variable so that it's x. So I'm going to have f inverse of x, and that's going to be x squared plus 2. So even though I'm using the same variable here, I know that it's a different relationship and it's an inverse relationship, and I can see that given the inverse notation that I have here. To prove to you that this works, let's go ahead and find f of 6. F of 6 is the square root of 6 minus 2. 6 minus 2 is 4, and the square root of that is going to be 2. So if my original function, I input some value, 6, and that function gives me an output value of 2. My inverse should do the opposite. In other words, I should be able to input a value of 2, and my inverse function should take me back to 6. So let's see if this works. What is f inverse of 2? Well, it's going to be 2 squared plus 2, and that, of course, is 6. So if you didn't believe me, hopefully you do now, that this is in fact the inverse of the function f. Now, I want you to write down the process that we went through. So notice the first thing that we did, before we did any work on our paper, we asked ourselves, what should the inverse function be? What type of a function? If we're dealing with a square root function, the inverse is going to be a square or a quadratic. Then I replaced my function notation with an output variable. So if I have f of x, I replaced it with y so that I could more easily solve for x. I'm switching the roles of the two variables. Once I've solved for x, I then have my inverse function. I just want to rewrite it using inverse function notation. So what I did was I rewrote the input variable as x and used inverse function notation to denote that that was the inverse of my original function. Okay? So I'm going to give you a couple to practice. I'll do the first one so that you can see another example, and then you can finish them out on your own. All right, so here are the problems that you want to complete. You may have already begun working on some of them. 1, 2, and 3 should not take very long. You should feel very confident about your solution. I will go over number 1 rather quickly, but the ones that you want to spend time with and that should take up the bulk of your homework time tonight is numbers 4 and 5. Incredibly important that you put time and effort into these two and that you come having completed number 5. If not, it's going to make tomorrow's class a lot more challenging. So make sure that you do so, and we will look forward to presenting these solutions tomorrow in class. With that being said, let's go ahead and take a look now at number 1. So if you haven't done so already, go ahead and complete it now. What I'm going to do is I'm going to rename the output, the variable y, and then I'm going to solve for x. In other words, I'm going to switch the roles of the variables, and that will leave me with x is equal to y squared minus 3. Now I'm going to rewrite this in function notation. So this is the inverse function of g inverse, and I'm renaming the input variable x. So it'll be g inverse of x is equal to x squared minus 3. Really important to remember that the inputs for my inverse function, what I can input for x, are all the values that I could have gotten for y in my original function. So with that in mind, that'll help drive your ability to complete numbers 4 and 5, and then ultimately to look at the relationships that we're going to talk about tomorrow.